Hello, everybody. This is Professor Tina Burns, and welcome back to the CS211 class. It is the summer 2025 version of Computer Architecture at Rutgers University. I am your host, uh, Dr. Tina Burns, and this lecture is Lecture 3B. It is the second lecture within week 3. So we have a few things to cover for this lecture, so let's go ahead and get started. So here's our roadmap, kind of to what we're going to talk about. We're going to go over computer architecture models, and this is a review from the previous session or the previous class. And we're going to go over that in the effort to understand storage and memory, and also we're going to go over control flow. All of that is leading us up to assembly language. And we're also going to talk about accessing the assembly console or assembly code. How do you get to that, and what does that actually mean? And then we'll end the class with something called GDB debugger, and I'll tell you guys what that is at the end. So let's go ahead and get started. So as you guys remember from the previous class, a ISA, it really stands for an instruction set architecture. And that is going to tell your computer, your compiler, how it should deal with specific commands and how it should perform operations. It will give things like order and how things should be formatted, specifically for the compiler and other operations on your computer. Now, this is going to model how the CPU, how the software controls the CPU. It's also going to set the instructions for the software hardware interface, and it really provides a user level interface to tell the hardware what it's going to do, right? Because it provides this sort of command set or format for the CPU, and we know the CPU is what allows us to kind of control this hardware. So there are two common types of architectures or ISAs that are used in devices today. There's something called the CISC architecture and the RISC architecture. So what we want to do is we want to understand the core concepts of both of these. CISC stands for Complex Instruction Set Computer, and RISC stands for Reduced Instruction Set Computer, right? So those are kind of the acronyms for those. For the rest of the slides, we're just going to refer to them as CISC and RISC. So when we think about CISC was a computer architecture structure that was really developed in the 1970s with the intention of reducing the number of lines or the number of things needed to represent code. Now, keep in mind that this is specifically for how you want to represent assembly code. So by having this, it allows us, excuse me, I'm sorry. By having this, it allows us to um, have an easier way to see what the compiler is doing. Now, the benefit of this is that it works well with memory, and it actually reduces memory because it simplifies these commands into basically assembly code. What that means is I don't need as much memory to handle all of the overhead from, for example, the higher level languages. So this is really good for reducing your memory, um, and it's beneficial if you're trying to do something that maybe you're going to need a lot of memory for, right? Which will lead us into determining what types of applications we want to use this for. Now, here's a sample instruction that you might see for the CISC architecture, right? And keep in mind that this is an assembly language. All right, so now, if you guys remember, we did talk about assembly language previously in another session. So what you'll see here is a simple add instruction that's written using this CISC architecture, right? And what we have here is the add, and then the two numbers that you are adding, right? Very much more simplified command. Now let's move over a little bit to the RISC architecture. Remember that is reduced instruction set computer. Now this was developed a little bit later, right? Keep in mind that CISC was developed in the 1970s, and then somebody came along and said, "Hey, we could do better." So they wanted to increase the speed and even make your sys a little bit faster. So in the 1980s, they came and developed this language to simplify sys. And what they found is for RISC, it actually works really well with registers. Now, keep in mind that we said sys is really good for memory, meaning you could do a bunch of stuff and you're going to use less memory than you would if you didn't use that architecture at all. For RISC, it is primarily focused on speed and handling commands quickly. And this is going to be a little bit better if you are concerned with accessing registers. Now, when we look at the RISC instruction, what you'll notice is that for the RISC, this is the same, pretty much a very similar instruction. The only thing that it's trying to do is add these two numbers, 1601 and 1600, or add what's in these two addresses. And what you'll see is that where in sys we had one line to handle this entire instruction, for RISC, we have 4, right? It needs to load all of these, load this one into an address, then it loads this one into an address, then it adds it, then it stores the result into a particular address in order for you to use, right? So what that means is that RISC is going to execute one operation at a time, whereas sys is going to do a lot more it can do more operations at once, which means that I don't have to take up as much time with memory, but it also means that you are not going to get the benefits of the speed of just handling a single process. So if we go back and we kind of look at sys here, right? Your sys, if you notice how this command is, it's going to be characterized by a large set of instructions. And it can operate it, it can execute it in a single instruction. So I can do all the things that I had in RISC in one single instruction. And again, its intention was to reduce the number of instructions for a particular program. And because of that, it can reduce the memory usage. RISC went the other way, and it wanted to operate or execute things more clearly, which means that I'm breaking down each of these commands into multiple things, but I can access the registers more easily, and I can perform tasks a little bit more rapidly. So let's take a look at that just a little bit more in detail. So your sys is going to be a little bit more hardware focused. Well, your RISC, some people consider that a little bit more of a software focused application. For your sys, you're going to be able to do a single instruction and handle multiple commands in that instruction. Just like we saw here, load this into memory, read the memory, add the two numbers, and then store it somewhere else. You're basically going to be able to handle that instruction or all those commands in a single instruction. Whereas RISC, what you're going to have with that is you're going to have smaller commands. There's going to be one command per line, right? One command per instruction. So sys, multiple commands per instruction. RISC, one command per instruction. Now, because you do multiple items with sys, what's going to happen is you're going to have a varying clock cycle per each command, right? If I'm storing this memory into memory address, and then I'm storing that into memory address, and then I'm doing something else, right? That's going to be 3 times the cycle of if I was just doing a single command. When we look at RISC, RISC is going to have 1 command per clock cycle. So each clock cycle, it's handling 1 command. Now, for your sys, it is going to have slower operation because it can do those multiple commands and within one instruction. And as we stated before, your RISC, because it's just doing 1 command, it's going to be faster in operation. Now, your RISC is going to have more registers, and your sys will have less registers, which also means you're going to have you're going to use less memory. Now, what are these 2 things used for? Well, your sys is typically used for like, oh, let me fix this really quick. Your sys is going to be used for low-end applications like, security systems and home automation. And RISC is going to be used for high-end applications, images, videos, etc. Now, where we see that today is your sys is used in some of the Intel x86 computers, CPUs. And by the way, as we do our assembly language and the bomb lab, we'll be primarily working with x86. Um, there are other versions, of course, that are going to be like x64, but we're working with x86, and that represents the fact that sys was created earlier, right, with an older architecture. You might also see this in kind of like the System 360 devices and the Motorola 68,000 family. Now, your RISC architecture is a lot more common, and that's used a lot more. It's used more often than sys, honestly, because of its speed and the ability to quickly access registers. But sys is still out there, still being used. You might see that in the RISC and the AMD. AM 29,000, ARM architectures, Power PCs. You'll see them used in a lot of your mobile devices, so your cell phones, tablets, etc. For your sys applications, you'll see them in gaming consoles, computer mainframes, and home automation. And RISC is going to be more for embedded things, automotive, applications, and mobile phones, as if I stated already. All right. So that's kind of an overview for the RISC versus sys, right? And now we're going into all of that. And keep in mind, this is with the intent to better understand assembly language or to better understand the bomb lab that you're going to be coding, right? So, um, I'm actually going to let me try something. I'm going to do assembly language now. All right, your programming languages, right? We have your machine language, the assembly language, and then we have your high level language, right? Your machine language, of course, is directly communicating with the compiler, with the CPU. Your assembly language is kind of this intermediary between the high level language and a machine language. And then, of course, the high level language. We have been working with high level language, right? C. And we already know what machine language is. That's already zeros and ones. Now we're really going to focus on this assembly language portion here, right? And your assembly language, why you would want to use that is because using your assembly language allows you to more easily access your memory and your registers. If you know what it is and what register it's at, for those assembly language, you can do and manipulate things with a lot more power and a lot more freedom because you know exactly where your registers and everything are. So that's why we do that, right? That's why you learn this assembly language and do all of these things for applications where maybe you don't want to use a high level language, or your high level language is going to have limits in terms of telling you exactly what memory address or register to gain access to. All right. Speaking of memory and storage, your main memory is of course going to have this large memory set. The issue with that though is it's going to be really slow to access. Um, but this is where a bulk of the programming information is actually stored. Your cache memory, now we have not gone over that, but we will in the future sessions. Cache memory is going to be a smaller set of memory that's an intermediary between your CPU and the main memory. It's close to the RAM. You can store data in there and you can access it a little bit more frequently. And then you have your registers. Now, your registers are a small memory set that have the fastest storage location, and they are right at the CPU. And this really allows you to access the data really quickly. So if we look at, let me try to draw something here. All right, so let's say we're looking at this from the top down, right? Uh, I don't know if I have enough room to draw here. Hmm. If I imagine this as a sandwich, right? This is going to be my RAM. This is going to be your CPU. Your cache memory is right here. This is where your program is accessing their data, right? It's saying, hey, I want to get something, some information from the CPU. It's going to store something here, right? Your cache is this intermediary where if sometimes you can look at your cache first and you don't have to worry about going to the main memory because if you can see this main memory is super large. And let me actually adjust this a little bit because it's really more like this. Your main memory is going to be extremely large. Cache is going to be somewhere in between there. Program accesses something from here in order to control the CPU. Your CPU has these things called registers, right? So your registers are going to be a lot closer. They're going to be somewhere around here, right? These are going to be your registers, which your CPU has direct access to and if you wanted to control that CPU directly, then this is where you'll want to talk, right? Maybe I don't want to go through my RAM or the cache or do all that because it takes longer. But if I know exactly what the register is, I can quickly access that CPU and get the information that is needed. So let's clear all those drawings. All right. So when we identify and we look at assembly language, we want to know kind of what registers is it going to, and also we're gonna need two things. What register is it going to, and what memory address is it going to? Now, we also want to understand a little bit about the control flow. So for every program that you write, um, like just so as I was showing you kind of what happens when you have this memory information and when you write a program, if you have a typically it's going to operate in sequential order, right? One, do this, do that, do this, do that, and do that, right? One, two, three, four, five. But you can actually adjust and change the control or the flow of that by putting in these if statements, these while loops, and these for loops, right? And all that will be in your program, and you can look at that and you can see those changes in this assembly code. So let's look a little bit at the programming flow. You have your C code, right? We've been talking about that already. That's compiled into an executable. Your executable is what allows the program to actually control the CPU. That then accesses your memory, right? It's kind of like a back and forth, access the memory. Hey, what is this? What is this number? What was stored there before? Let me store this in here. Add these two numbers together. So it's kind of like this back and forth relationship between the two. And then that goes back and forth. That memory information goes back and forth between the CPU. And as I stated before, kind of as I showed in that diagram, your registers are going to be somewhere in there, right? So that you can quickly access all of this information as far as the CPU information, right? All right. So this is kind of our flow, right? And this helps us to understand what we're doing with assembly language. Assembly language is going to be right around here. It's gonna be right here, right? Where you have more control, more direct access to the CPU. You can see the memory, you can see the registers. This is exactly where it's gonna be. Whereas when you write your source code is here, your executable is here, and your assembly language is here. So We haven't gone over that, but we're going to go over it very, very briefly. We're going to go over it very shortly. So this is your uh, test. This is your dot C. This is your dot out. Although you don't necessarily need to call it out, we have been traditionally calling it here for this class. And this is something we're going to call a dot S file or your assembly language file here, right? So this is your source, this is your output or executable, this is your assembly code. And this is kind of how it flows when you think about like your actual programming flow. All right. So let's talk a little bit about how all of this works in terms of you controlling everything. As a programmer, you are dealing with data and instructions, right? We have two main things you're dealing with, the processor and the memory. For your data and instructions, you need to access your memory. Your memory is going to tell you what you're doing, what the processor is doing. And then, of course, your data is going to go into the cycle where it goes back and is stored back into memory. All of this is super important because this shows us how we're doing control and how we are moving forward with those other items. All right, so let's get a little bit more into the assembly language stuff. All right, keep in mind that what I showed you guys previously was that assembly language code for if you're using CISC architectures. So here are some of the common commands that you see, particularly if you're using x86 or the CISC architecture. You might see something for that says move, which is going to transfer or moves data from one memory address to another. Load or store. Um, will allow you to load things from memory and registers. Add, of course, is going to add numbers, subtract. Jump is what allows you to skip to a different program address, right? So your jump, right? This is typically how we flow here. Your jump will allow you to go to a different area in your program. So you say, that's typically like, okay, you have an if statement. If this happens, then do this. Your jump in assembly language will help you see kind of where that goes. Comp is going to be for comparison. And then, of course, down here, you have your binary operations. Now, a few other things that you're going to see in assembly code are these identifiers here. Your register destination index, register source index, and then also your base register pointer and stack register pointer. Um, so these are kind of your common commands, and we'll go over a little bit more of that in the upcoming slides. All right, so let's take a few minutes and let's look at a sample program and what that looks like from assembly code to this other code that we're discussing. So, oh, I do want to make a note. So, I know for the past couple classes I was using Windows subsystem for Linux and doing the programs there. Today I'm actually going to use mobile xterm and I'm going to SSH, excuse me, into the iLabs computers. Now, mobile xterm has been really good for me in terms of using that and getting into our to the systems. And it is a free software, which is why I really use it. I like having it because it will store and save your sessions. So I'm going to go ahead and log in. So this is basically taking the place of the Apache server for me today. I am going to open up multiple windows, similar to how I had the terminal in our in our first week sessions of class. So that's what I'm going to do here. You'll see me opening up this terminal, da da da. All right, and then let's go back and I'll open up one more. All right, so that's just getting us set up to where we want to be. And if you look at this, you'll see it kind of has my same desktop and home directory for my standard usage. So let's go ahead and get into the files that we want. Teaching CS211. Okay, I'm going to go ahead and make a directory for week 3. And I'm going to copy my make file into this. Let's go with okay. Oh. Uh, I'm going to copy my make file into this week 3A class that we just created, and then I'm going to go ahead and move into that. All right. We're going to go ahead and move there to teaching CS211, 2025, week 3A. All right, that's one window, and then we will also move it here. And again, I'm doing this just to kind of set up our platform. What we want to do. Okay, so I'm going to make this first window my make file. I'm going to make this second window the code that I want to use. So we'll call this assembly test. Um, all right, so now we've created that file, and this one will be kind of my execution window. Let's clear that so we're at a clean slate. All right. As you guys already know, the first thing we're going to do here is we're going to include our necessary libraries. All right. I always like to comment so I remember what I'm doing here. And then we're going to start with our main function. And we're going to create here, it's a very simple function, addition function that will allow us to see what happens when we have assembly code. So this we already know. We have int main here. Okay, now what happens if let's do our return statement, exit success. All right, we have that here. Okay, I'm gonna set up an integer to, ooh, let's make sure we actually write that correctly. Int b is equal to 3. And then integer c is gonna be a plus b. And what we're gonna do is we're gonna print out to our screen. Um, A plus B is A plus B is gonna be D. That's gonna be what we would print out to our screen. And we're gonna do a new line character here. Okay, so we have our code. First thing we want to do is let's go and see if we can execute this or operate this, right? Um, the file that we're going to use here is going to be what we're calling this here, assembly test.c. Oh, assembly test. Let's go ahead and save that, and you'll see it did write those lines of code. So the first thing we want to do is see if we can make it, and it did in fact make it. Let's go ahead and execute that. It executed it, and it'll tell you that let's go ahead and change that. Should be A plus B, not A equals B. Aha. All right. So that's gonna be A plus B. Okay. All right, and now we know that our code works. We can make it again and then execute it if we wanted to. Uh, let's go ahead and do that. All right, so now we have our code sample that's right here. This is your machine language. This is your high level language written in C, right? But let's say I wanted to view this in assembly code. There's one easy way to do that. And before we even start, so let's look at what we have in our directory right now. We have this assembly test.c and .out, right? Out is our executable file. Now, if I wanted to create or get access to the assembly code, you can do this with the GCC does allow you to create that. And you're going to do this with this command. It's called GCC-S. This will create an assembly output of your file. And then it should be GCC-S, and then whatever your code is. All right, so let's do assembly.c. All right, now look at that. Oops. And you'll see that it has created this -s file here, right? So let's go ahead and pull that up. This is your assembly language of this file. All right, so this is what it is as assembly as a higher level language, and this is what it is as assembly language, which is the intermediary between the higher level language code and your machine learning code, your machine language code. So now let's go back to the slides and let's go ahead and look at this kind of in a little bit more detail to see what does each command do and where are we looking at there, right? So we'll go back, I'll go back here. This is our main function. I might have did it differently, swapped the numbers around a little bit. Let's do something as we're here now. I'm going to go back and I'm actually going to just copy this code in just so that we're at the same page, right? Actually, no. Let's go ahead and make this. We're going to update this. And I'll tell you why, because it's going to make it a difference the direction that they're located in the assembly code. So I want to make sure that we are in the right direction here. All right, 3 is first, 2 is second. Let's go ahead and save that. Let's get out of here. Let's go ahead and make this. Let's just make sure we can execute this again. And it does. And then let's go ahead and make our assembly code C. And then now we will go back into that file. Okay, so here's your assembly language code of this particular item, right? So now let's go ahead and look at this in more detail. So here's our program, very simple. You have your libraries, you have your function that's called main. You have three different variables that are being stored into some sort of memory address. Your first variable is going to be 3, your second one is going to be 2, and then this is uh, a combination of these two when you perform some sort of function. And then you have this here, which is just a string variable for what you're performing there, and then of course the return. Now, we already went through, this is how you would generate your assembly code, right? Using your GCC compiler. Oh, I do want to make a note that different compilers will display information that's slightly differently, right? So if you're running a different compiler, or you're running a different version of GCC, or maybe you're on a different platform, it may not look exactly the same as the code that you see here. Even when I generated this and I did this in my Linux subsystem on Windows versus when I'm doing it in iLabs, you see something a little bit different each time you run it. All right. So the first thing we're going to see here is at the top of that, and let me just pull up this one more time. You'll notice that at the top of this right here is where we see the name of our program. All right. This is our name. It's telling you that it's a string. The next thing you're going to see is this next section is telling you something about a memory address. This is saying that this section of code, this item right here, is going to be dedicated to this particular memory address. So it's going to store this string in a memory address, and the way that I'm going to access that symbolically in my program. So it's basically you can consider it like a variable, but it's a symbolic representation of this section of code. So this LCO, anytime I see that, I can symbolically say I'm going back to this section right here, and this section is actually storing this string into this particular into some sort of address that I'm going to use and print later. All right. So this is saying that this is a string. Keep this guy here in mind. All right. The next thing it's going to do is set up this global for your main function. It says your function. This is a function, and the title of it is main. And now when we get here, this main has its own symbolic representation, which is this LFB6. So anytime I make a reference to this, that is saying I'm going back to, or I want to get access to my main function. All right, now, once we do that, now we're going to go back into this. So keep in mind that this looks a little bit different here because I did it with a different set of code, but don't let that confuse you too badly. All right. Local label for your data frame or symbol for your data frame, that's going to be the same here. Now, here is it's doing this process, and what it's doing here is it's just starting the call frame for debugging, right? So since I'm using this assembly language to debug information, this is just telling me that I'm starting that stack. I'm starting this to debug it, right? Now, here's where we get to the interesting part where we're dealing with registers and information and all of that. All right, so we are dealing with a X60 X86 frame for memory. And what this is doing for us right now is it's saying that I have something in my stack, right? Meaning that I need to access and get this information from memory. In order for you to access it, you need to tell me how much do you want to get. So this line of code right now says this sub q means that I'm taking 8 bits from my stack mainframe in order to use as a pointer. And this pointer is going to allow me to have space for my local variables. Now, remember back when I talked about the LCO? The LCO, remember from back here, was this string code right here. This is my string right here. Now, I'm using that symbol and I'm getting back to that, and is allowing me to store this. Oh, I see where I wrote that. that information is allowing me to access that from my previous portion of the code. And what it's doing is it's storing this into this register. So it's taking that, I've got this input A plus B is C, and I'm storing that into this register. All right, now we have another command here. So register. Where what it's going to do for this one is clearing your register, meaning that you are getting rid of the information there, and you're storing the data, and this is allowing us to add 8 bits back to that register. Now we're going to go through a couple of these, so it'll make a little bit more sense here, but this kind of just goes through some of those commands that you're seeing in your assembly language code. All right, now there might be additional information at the end of that, at the end of your assembly language, and what that does is that just basically tells you more data about the processor. It tells you more data about your about the compiler and different information there, right? So this is some of this random different things that are used here. All right, now what I wanted to go to or through, we didn't go over that, but ooh, man, okay. Here's where we get to the portion where we're storing information into the registers. RBP and SP and all those, they're gonna have some significant meanings, right? Your RBP is gonna be your base register pointer, and what it's doing is you'll see that these two variables, 3 and 2, or these two values were my initial the values of those, right? They were the values of my variables. We had A is equal to 3 and B is equal to 2, right? So this is storing A into this at location 12 for this particular one, and this is storing B at this register address or this memory address, right? At position, it's dividing up this register into different spots, right? If these are each going to be 8 bits long, what you're going to do is you're going to take this first portion of it, or I guess technically it's 4 bits because this is storing it at 8 and 12. It's going to take a portion of that and it's going to store it at position 12. And then the next portion of that is going to store this at position 8, right? Position -8. And that's pretty much that portion of it, right? So now that we've gone through that, let's go ahead and look at this guy. You've seen these commands. Now, what are those common commands that you'll see is you saw where it kind of had this MOV that's going to move data to another location. So where I said before that this is clearing your register, if it's making it a 0, it's basically clearing it so you can add additional information in there. When you have load or store, that command is going to load data between your memory and your registers. Add, of course, is going to, as it said, add information or add data. Your sub or subtract is going to be used to perform some sort of arithmetic subtraction of two variables. Jump is what we use when we want to change the order or the control flow of our program. Compare, you're going to compare two operands, or that's like if A is equal to B, then do this, right? That's what you'll see for this compare function. And then of course, these 3 items down here are what you would commonly see even in the upper level languages for your binary operations, comparing it like and, or, not, or, etc. Now, what you'll also see, what we're not as familiar with, is these and I'll pull up our code again, right? And let me make this a little bit larger so we can see it. See, notice how we kind of have this RBI and all of this information, RSP, et cetera, et cetera, et cetera, right? So when we have this RDI, that's going to be your destination index. That means where is this going to? And it's typically going to be used for your first function in the argument. You're going to generally, you'll see that first. Your registration source index is what you might use for your second function, your second operation, right? So typically you'll see the RDI first and then the RSI first. RBP is going to be your base register pointer, and that is going to start the stack. It's going to indicate where that stack starts. RSP is going to be your stack, and that's going to be the lowest address for the current stack that you're working with. And then your RIP is going to be for your instruction, or it's going to be talking about your instruction pointer, and it really is going to tell you where the current execution of the address is. All right. Now, notice how we have these RDI, RPI, RSI, RSP, da da da. If we break this down a little bit further, I means it's a placeholder. You're going to keep that there until you have some information. Key is a pointer, and X is your actual arguments. So again, if we look at here, right, we'll see that kind of executed. X, these are your actual arguments, right? It's adding these two because these are your actual arguments. And again, if we look at this kind of RSP and RBP, right? You have your RBP, that's going to be where you're putting your base pointer. This is going to point to where these are in memory. All right, so we went through this, right? And we were able to access this previously with which command? The compiler command. I'm actually gonna set up one more window. I'll get out of here. All right, so we use this GCC compiler -s assembly test.c in order to get a quick and dirty way for us to see the assembly code and kind of print it out as a text file that we could read. But there's also another way that you can access your assembly code, and this is more common using a tool called GNU Radio Project Debugger. Now, GDB is very commonly used. In fact, it is typically used for when we want to debug our code. So, typically in this test class, what we might be doing is just going back and forth, compiling the code, and then going through it line by line and determining where the error was. What you don't want to do, that's not necessarily the best way to do it. Instead, you can use this debugger tool, which will go line by line through that and allow you to kind of debug a little bit more easily and efficiently. We're not going to do that today. We will go over that in terms of debugging, but one of the other features of this is that it also allows you to get the assembly language of your code and to view it in different aspects. So if you wanted to start GDB, the first thing you can do is you can just type in GDB in the in your mainframe, and you'll see that kind of come up. So why don't we go ahead and do that? Maybe if I actually put the right thing in here. All right. Now what you'll see is I just typed that in, and now I am in this debugger mode. Right? I am now no longer kind of in the main Linux outside of this, but I am now in a debugger mode. So anything I'm doing here is going to be inside of my inside of this debugger program. All right, so it helps you to do some debugging. Now what you can do is when we have this G, you'll notice that every time we every time we compile our code, we've been putting this -G in front of it. And the reason we put this -G is because we want the option to be able to use this debugger code, this debugger option here. Right? So you will only have access to the debugged version of your code if you compile it with this -G thing here. And also, as a note, when we're accessing this file, we're accessing the compiled version, not the C code, but the compiled version of that, right? Which is what your compiler, what your CPU is looking at. Now, how you're going to get to that? How do you get to your code that you're debugging? You're going to do that by typing in the gdb command and then whatever your executable name is. All right, so right here, what we did was we just accessed the GDB kind of front panel or home screen. Let's actually get out of this. All right, I can just type in this exit command to get out of there. And let's go to GDB. And let's access that. All right, now what this means is I am now inside of GDB and I am looking at my assembly test.out file that I have just compiled, right? So we went through that. You saw kind of where that was if you wanted to get the main information from it. Now, there's a function in GDB called layout next, right? And you can type this right in your commandment. Now, keep in mind, you're typing this after you have already accessed your assembly file, after you have already accessed your executable file. Inside of that, you can go ahead and look at your code here. All right. And look at that. I can now see my assembly code. What is this telling me? This is looking at my code from pretty much beginning to end. Now, this is going to have, as you can see, a lot more information than what we had when we compiled, when we output it using GCC. Right? It's going to tell you kind of where your registers are. It will tell you where you're calling. It's telling you what you're jumping to, et cetera, et cetera. But it still does have this main. Let's see if we can find it. You're going to have that portion where you store your information into those addresses here, and you can kind of follow through and see where that data is. All right, so this is going to give you your main code, and then it's also uh, it gives you a little bit more detail here. And what you'll see is that these numbers R3 and R2 is telling us that we're moving in these particular addresses for memory for the stacks there. So this is storing my A, this is storing my B. And then it's gonna take this guy and go ahead and put it into this memory address. Now, what I want to show you guys also is that we just executed this layout next command. If you press enter again, what you'll see is that it'll give you the original code at the top, and different items like that. All right. So these are just different views. We're gonna go ahead and exit here to get back to our main function. And I just want to end the class by giving you kind of some common commands for your debugger here. That's your layout next. Oh, I don't have the commands there. Okay, I'll go over the commands in next class. But we just went through kind of some of the sys code, right? Where you might see the different items there. So here's like a sample sys code, and you'll see where it's trying to perform a particular thing. It's going to subtract these two. This one is going to take this and move these to a particular action, and this is gonna test it out, then it's gonna jump back. Um, in my RISC code, you'll see slightly different commands. Like it's going to adjust the stack pointer, load the target address. So you'll see your RISC code is going to be a little bit different than you would have for your sys code. All right, I will definitely go into more detail as we continue with the next lectures. Thank you all for joining me, and until next time, enjoy the rest of your day.